Okay, this is section 4.3, modeling exponential data. Okay, recognizing exponential data. We need to recognize whether or not it's going to be appropriate to use an exponential model. Well, of course, one way is to actually graph it and see if it follows one of those two curves we had way back in section 4.1. So we need a way to recognize when an exponential model is appropriate for a set of data. Remember, for linear data, it was the first differences that we calculated. And if the first differences were all equal, it's exactly linear. If they were approximately equal, then it was almost linear. Remember, that meant the second differences had to be 0 for exactly linear or almost 0 for almost linear. It'd be nice if we had a rather simple test like that for exponential. So now we still require that the consecutive independent values all differ by the same amount. Remember, that was actually called they were uniform. Now, if the data are truly exponential, which would mean that they're exactly exponential, then when going from the current value of the dependent variable, it must be multiplied by some fixed constant in order to get to the next value. Now, for multiplying by a fixed constant to go from one value to the next, that means the ratios of consecutive dependent variable values must all equal the same number. Okay, so if you look at ratios of consecutive dependent value variables, so that means the y's. You look at the ratios of consecutive y's. If they're all the same number, the data are exactly exponential. Now, by looking at the ratios of consecutive dependent variable values and the value of delta x, we can also determine the base of the exponential function. Remember, the delta x is the difference in the x's. Remember, they're all the same. The base of an exponential function is the value that is taken to a power. So it is the number that has the exponent. So for instance, f of t equals 4,000 times 1.4 to the negative 0.11t. The base is 1.4. Remember, the 4,000 was the initial amount. In g of t equals 300 times e to the 2t plus 5, e is the base. Remember, 300 is the original amount. So we have a way to get the base. Hopefully the problem will tell us the initial amount, or if it doesn't, maybe in the table it has a value for t equals 0, and that's the initial amount. So the test for exponential data. For a set of data in which consecutive independent variable values all differ by the same amount, the data are exactly exponential if and only if the ratios of consecutive dependent variable values are all equal. Now, sometimes it's kind of obvious that to go from one I value to the next one, you multiply by a simple number like 2 or 3 or something like that. So sometimes it's kind of obvious. And other times when it's a really bad number like 0.73, you might actually have to do the ratios. Now, furthermore, if the consecutive independent variable values all differ by delta x, and the ratio of consecutive number variables is r, we're using r for ratio, then the base of the exponential function that models the data is given by r raised to the 1 over delta x power. That's basically the growth factor, or the decay factor if it's decreasing. Remember, here r stands for ratio. In this section, we will look at data that are exactly exponential. In the next section, which would be 4.4, we'll look at ones that are approximately exponential. So, some examples. Number 1 says, a room is at a constant temperature of 72 degrees. A steaming cup of hot cocoa is brought into the room, and the difference in temperature of the room and the hot cocoa is recorded every minute. The results are given in the table below. Answer the following. Round all final values to 2 places to the right of the decimal point. In Part A, determine if the data are exactly exponential. Question B, find an exponential model for the difference in temperatures between the room and the cup of coffee. Part C, use the result of Part B to find a function capital T of t that gives the temperature of the cup of cocoa t minutes after being brought into the room. Remember, B is the exponential model for the difference. C is going to be the function for the temperature of the cocoa. In Part D, After approximately how many minutes will the temperature of the cup of cocoa be 80 degrees? Okay, now again, I've got my time in minutes going from 0 minutes when I first went into the room out to 5 minutes later. And here are my temperatures, the difference in temperatures between the cocoa and the room temperature. So this is clearly cocoa minus room temperature. Remember, the temperature of the room is kept at 72 degrees. Our solutions. Okay, in part A, we first note that delta T is equal to 1 for all the values of T. Remember, we said we recorded the temperature at the end of each minute. So again, if you go back to the data, we can see that. It says we need to compute the ratios of successive values of D to see that they are equal. So I'm going to set the float on the calculator to 2. Okay, so let's take out the calculator. Float, so go to mode, scroll down to float, go on over to 2, press enter, and we'll quit that. Now for convenience, I reproduced the table again. So here's my time, and here's the temperature difference. Okay, we have the following table for the ratios. And when we do the ratio, it's going to be like we've all doing all the others, right minus left. We're going to do right over left. So the time increment and the ratios of D's. Okay, our first time increment, we're going from 0 to 1. The ratio is 120.4 over 140, which we get to 0.86. Again, you can just verify on that on your calculator by really doing that. 120.4 divided by 140. And again, to two places, it is 0.86. Our next time increment is from 1 to 2. We're going to look at 103.5 over 120.4. It works out to be 0.86 again. Again, you can verify that easily with your calculator. 103.5 divided by 120.4. Okay. The next time increment is from 2 to 3. The ratio is 89 over 103.5, which is also 0.86. Again, I will leave that to you to verify in your calculator. The next time increment, 3 to 4. The ratio, 76.6 over 89, which is also 0.86. And again, the last time increment is 4 to 5. The ratio is 65.9 over 76.6, which is, of course, 0.86. Again, you can verify all those on your calculator. Notice they had to be, because otherwise we couldn't continue with the problem. So we verified because all of the ratios, the consecutive D values, are all the same number. That means the data are exponential, exactly exponential. Remember, this is just out to two places, though. So we've determined that the data are, in fact, exponential. Question B wanted us to find an exponential model for D. So delta T was equal to 1. Remember, we took it every minute. So the ratio that we found in part A is our base. Okay, remember, R is going to be, or excuse me, the base is going to be R raised to the 1 over delta, in this case, delta T power, so 1 over 1. So at T equals 0, D was 140, right? Go back to our table. Yes. Okay. So here was our ratio of 0.86. So the A, you remember, the base of the exponential is the R raised to 1 over delta T power, so 140 times 0.86 to the T power. That models the difference in the temperatures. It doesn't model the cup of coffee, excuse me, the cup of cocoa's temperature. That's part C. So for part C, recall the temperature of the room was a constant 72 degrees. Now remember, this is the difference between the room and the cup of cocoa. So temperature of cocoa, the temperature of the cocoa minus 72 is D. Okay, D is this thing, and remember we're calling the temperature of the cocoa, we're calling that capital T of T. So capital T of T minus 72 is equal to 140 times 0.86 to the T power. Okay, so D of T, replace it with what it is. Remember, T of T is the temperature of cocoa. This is the difference. So T of T is going to be 72 plus D of T. So 72 plus 140 times 0.86 raised to the T power. That's the temperature of the cup of cocoa T minutes after you bring it into the room. And remember, just from our experience, the limiting value is going to be room temperature with 72 degrees. Question D, we want to know how long before it's cooled down to 80 degrees, so we want capital T of T to equal 80. We want this expression to equal 80. So we're using crossing graph method with y1 being T of T and y2 being 80. And there's going to be my window, okay, because I'm hoping it can cool down to in less than 20 minutes, but you never know. And my 100 for the max on the temperature is to go slightly higher than the 80. Okay, so let's go ahead and put this into our calculator. Remember, originally the calculator had the D of T in it, or no, it didn't have anything in it because we're calculating ratios. So let's see, did it have anything left over from the previous problem? No. So T 72 plus 140, open parenthesis, 0.86, close parenthesis, raised to the T power. Get out of that. And we want that to be 80. Now let's go to our window. Okay, 0, 20, 2, 0, 100, 10. Okay, and then second, calc, choice 5. Okay, that's going to graph them. Okay, remember that's the temperature of the cup of cocoa. And there is what we want it to be. Ooh, we just barely got it on the screen, didn't we? So that is correct y1. That is correct y2. And let's guess away. So in 18.98 minutes. Remember, I had my float set to 2. That's why I'm only seeing that many decimal places. So here I didn't have my float set to 2, so 18.977, which to the nearest hundredth is 18.98. Let's see, and then we were supposed to round to 2 places, so 18.98 minutes. Example 2. Peter Piper picks peppers at an ever-increasing rate. The number of quarts of peppers that Peter picks each day since he began picking peppers is given in the table below. Answer the following. Round all final answers to 2 places right at the decimal point, except in part C, round to the nearest whole day. Okay, question A, show that the data are exponential. Part B, find an exponential model P of T that gives the number of quarts of peppers that Peter can pick T days after he first began picking peppers. And question C, after how many days since he first began picking peppers will Peter pick 50 quarts of peppers? And notice T equals 0 is when he first began. So it's kind of like he was a rookie then. So my days are 0, 4, 8, 16, and 20. Notice they're 4 days apart. And my quarts of peppers is 12, 16, 21.2, 28.2, 37.5. Okay, our solutions. Okay, we want to reproduce the table again. Okay, so there's the table. Okay, we do observe that our delta t is 4 in all cases. Remember, if they weren't all the same, we'd actually have to plot the data to see if it looks like it's exponential. Okay, we're now calculating the ratios of consecutive p-values. Okay, again, we set our float to 2. Since it's really just, division, 0 to 4, 4 to 8, and so on. I had 16 over 12, which is 1.33. 4 to 8 was 21.2 over 16, which is 1.33, and so on like that. So again, you can easily verify these on your calculator. It's not really difficult calculations. But anyway, we do see that all the ratios are the same. They're all equal. So that means the data are, in fact, exponential. Which again, they had to be, otherwise, we couldn't continue with the problem. So we've done the verification for part A. Okay, part B, okay, we want to find the model. Okay, our ratio, again going back, our ratio was 1.33. Our delta t was equal to 4. Okay, remember, the r is 1.33. Remember, A, the growth factor, is r raised to the 1 over delta t power. Okay, so if you do that out to 2 places, again, take out the calculator, okay, quit this, and do 1.33 raised to the 1 divided by 4 power. Now remember, in the TI-83, you're going to need to put the exponent in parentheses, okay, because the exponent has an operation. So 1.07. Remember, I did set my float to 2. Okay, so 1.07. So do we have the value at t equals 0? Let's go back to our table. Yes, we do. 12. So our model is going to be p of t is equal to 12 times 1.07 raised to the t power. Question C, we need to know when p of t is equal to 50. Okay, so it may take several days, so I had my windows go from 0, 100 to 10, and the y value of 0, 60 to 5. 60 is slightly bigger than what I wanted. Okay, so after doing all that, I didn't do it by hand again for you, because we've done it enough times. We find the point of intersection to be 21.09. So to the nearest whole day, 21 days. Whoops, there. 21 days. Now some people would say it's not until the 22nd day that he actually picks 50 quarts, but if we round, 21 days. That is the end of section 4.2.